Morning, Kelvin. Doing okay?
Yeah, I'm doing pretty good. Quiz wasn't too bad this morning. I I'm still having a little bit of trouble finding that RSP value the just for the different one, but I
Okay.
mean I can figure out everything else, just that RSP.
The is it the RS part or the RP part that gets you?
Well, okay. The RP part is pretty easy because you're just giving us a point, and
Yeah.
that's that. Um, I guess it's the RS because with the sheet it changes depending on where you're at.
Hmm.
So I that's just X and it's just the two variables, right?
Yeah. So yeah, yes. And really that's not that much different than what we did with the Coulomb law either. So with when you're looking for that vector that goes from the origin to a source, it just means like think about where if you're doing Coulomb, where is the source of the charge, and then really too if you're doing the this Biot-Savart, you're also asking what is the source, where is the source of the moving charge. So um, in both of those cases, right, if you have a volume or a surface, it's changing on that volume or surface. So you'll need some kind of variable that can change. And that's where where that comes from, where it's like you write the vector with variables in the vector. And then the point, usually we don't have it changing, but you could use a variable for the point as well, but you usually want to use a different variable for it since that's not the one you're integrating over. Yeah.
Right. Yeah. It's just I think the hardest part is I get all caught up in like because to me DX or like the DS that's the change in your field, but I guess when you write the source, you have to put in the variables or else you won't be able to integrate anything. So
Yeah, if you don't have variables in that RS vector, it will be your vector won't ever change. It'll just be from the origin to one single point. Yeah.
as far as like so I know how to set up the integrals, but like how far do you want us to simplify them? Because I just left mine as a cross product because it really
I yeah. In this case, like on this one, I think you should have been able to find the result of the cross product of those two vectors. So um, I would have liked the cross product result on this, and on like the next exam, that's what I would like. So if
okay.
you got to the point where you set it up, yeah, I mean, I'll probably have to take a few points off, but it's not going to be like
No.
half of them or something.
Yeah, that's fine. I completely understand that.
Because the reason too is right. What is the can you tell what does that cross product tell us? What would you describe the cross product as telling us?
It's like telling us the strength of the magnetic field at a certain point, right?
So yeah, it will give us a magnitude. What else will it give us?
Um, oh,
I think you're close to saying it.
it'll give us the direction on it.
Yep. Yeah, it's a vector, right? When you take the cross product, you get a vector. So you get a magnitude and a direction. Let me see. I'm trying to pull up the cookbook here so we can look at it together. Okay, here it is. And the reason that that's important is because right this is where it diverges between Coulomb and Gauss, is when you get down to here, right? Coulomb and Biot-Savart. In Biot-Savart, the direction depends on the cross product. So this one is going to be a perpendicular result. And for the electric field, though, it's going to be, it's not going to be a perpendicular result. It's going to be a collinear, I guess, result. Let's pull open the Gauss one. Right, it's in the E field is in the same direction for Gauss and Coulomb. So that is the big difference. Is Biot-Savart it turns out, right, this magnetic field is always going to be perpendicular to the direction of the movement of the charge, which is all what, right? Because current is moving charge. Current is moving charge, and the H field will be perpendicular. I know it gets a little, this whole class, it's a little weird because you are kind of forced to do a lot of vector calculus. I think everyone is like, after Calc 3, they're like, oh, great, I won't have to think about that again. But electrical engineers definitely do. And then depending on, you know, if you're a mechanical engineer that does a lot of fluids, you're going to have to deal with it, or a nuclear engineer that does a lot of fluids. So I don't know how much we'll get into this later, but you probably talked about the wave equation in one of those classes? Does that sound familiar?
I remember briefly looking at it in like Calculus 3, but we didn't really go into too much depth on it.
Yeah, and we probably won't here, but the reason for it is that wave equation comes up in a ton of different fields. So the wave equation, you know, it guides electromagnetics, fluid dynamics, heat transfer. It also comes up in quantum physics a lot also. So with like the energy states and like where the electrons will be. So anyways, it's kind of hard to like pull all of this together well in one class, but that's why things like the Laplacian like keep coming up over and over, is because it's part of this really traditional way that all these fields had that equation in it. And initially, like 100 years ago, right, they didn't have computers, and so they were able to come up with that equation, but they couldn't necessarily easily solve it for each like situation that they had, but they would try. And then somewhere along the way, guess my video maybe paused, but somewhere along the way, right, we got to this point where now we have computers and we can get solutions to a lot of these problems by solving the wave equation, but we have solvers that can do it for us now. And so that's always like the challenge with like undergraduate education is, how do you like teach the classical reasons that people care about this stuff and still like show the way that we use them in modern applications. So yeah.
I just had one more quick question. So I know that you've created like a Biot-Savart and all the other cookbooks. Are you going to create one for the Ampere's law, or is it because it's similar to enough of them that?
Yeah, I did not make one for Ampere's law, and I wasn't necessarily planning on it. I might get around to it, but it's very similar to the Gauss's law one. I think I might have. It's been a while since I have a lot of videos in my YouTube channel now. I might have an older video where I do like a pretty concise explanation of Ampere's law. So let me still have a few minutes before class starts. Let me see if I can look in my videos and see if I had a good one. It's hard because there's not, as much, like in my mind, like for Ampere solving these like symmetrical problems, there's not as much of a cookbook as much as, yeah, no, I just did the Gauss's law one. Okay, that's a good point. I will put it on my list of things I might try to get done.
So okay, sounds good.
Either make a cookbook or make a more condensed video, like a 15-minute video where I try to explain the steps better, or maybe not the steps, but the way the method is. I also think, to me, it's a little trickier because with both the Gauss and the Ampere, like you're relying on all these symmetry cases. And so like to some extent, there's always like, you need to look at the whole thing and figure out what the symmetry is, which is a little harder in my mind to translate to a cookbook. Whereas like with those the Biot-Savart and the Coulomb, like those ones are the same like every time, because no matter how, like those ones they can give you the H field or the E field for any situation ever, based on the vector directions that you've come up with. And so that the cookbook is a way of figuring out what those vector directions are, and you'll always get it right. You might come up with something that's really hard to solve if you're in a weird coordinate system or have a strange object shape. Like, yeah, you might get something that's very difficult to solve, but it will always be correct. Whereas with the Ampere and the Gauss, like, yeah, you kind of need to relies more on determining like that you have the correct symmetry. So. All right, welcome everybody. Calvin and I have just been talking about Ampere's law and Biot-Savart law. So how are you all doing?
I'm good. Dr. Chrysler, my system was slow, so I uploaded the quiz like a minute late.
Okay.
That's
all right. Yeah, thank you for letting me know. Yeah, sometimes that might happen. All right, so pull a couple things up. Is it snowing in Pocatello?
No.
No, not at all. Wow, it's coming down pretty hard up here this morning.
Yeah, it's snowing in Blackfoot, actually.
Yeah, okay. So maybe it'll make its way down to Pokey. All right. So I do not have a lot of announcements today. The main one is, right, we're on homework 6. Homework 6 is due on Tuesday. And so next class, you'll also have a quiz and a homework due. So you'll have that on the next class. We are very, very close to beginning to talk about the project. Okay, so this is, I think, the last day of electrostatics. So we'll be, the next step is to move all of this into the time varying systems. And so when we do that, we will, that's what the project is going to be based on, is time varying system. So we will be talking about the project, and I will probably 1 week from now is probably when I will introduce it. So after we've done 1 day of electromagnetics, so that you have a little bit of a handle on what we're talking about with Faraday's law. So next Tuesday, we'll start talking about Faraday's law. Next Thursday, I'll introduce the project and lay out all of the due dates and all of that. So that's about to, well, we're about to get started on that. And besides that, I don't have anything. Oh, actually, I do have one more thing. I looked yesterday evening. I don't think, okay, great. I have one response for the mid-semester feedback. And if you would like to give me some feedback, which I would appreciate, then please feel free to look on the Moodle page and give me a little bit of extra feedback, and I'll see what I can incorporate into the class. So that is, again, just to remind you, if you look right here. So at the very top, just scroll down a little ways, and we have the mid-semester feedback right here. Okay, any questions, comments, thoughts, ideas from all of you? All right, well, then let's look at the, let's do some homework. So homework 6, let's spend a bit more time. There's another problem, and it's on Ampere's law. I think, you know, the Ampere's law stuff will be more difficult than the last two problems, which are boundary condition ones. So let us take a look. All right, can you all see the question 2 in the PowerPoint? Yeah. All right, perfect. All right, so we have an infinitely long cylindrical structure. The z-axis is out of the paper once again. The inner shaded region is a semiconductor with current density. And the region between the semiconductor and the grounded metal cylinder is free space. Okay, there's also a current, another line current that is located at 2,2. So this point here, and it is also going in and out of the page. And we want to find the magnetic field in the following regions. So we want to be able to find the magnetic field basically anywhere. All right. So the first step is to find it inside of this semiconductor. So that's this inside of the semiconductor is here. And in this case, right, what method do you think we could use to find inside of the semiconductor? So I guess we have two choices, right? One is the Biot-Savart. And 2 is Ampere. So what do you think would be the best for inside of the semiconductor? So how about this for the, give you another little hint. We got, this is how we find the H field, right, with Biot-Savart. Or we can use the other relationship, right, where we had this. Does this look correct? Oops. So there's one thing I did wrong, right? So which one of these do you think is easier to solve for this, if we're just looking inside of the semiconductor? Yeah, I think I heard Ampere's law, right? So if we make a contour path, right, around here or even inside of here, right, it's easy for us to make a contour path, right, like this, where we can get this current. And also, right, we expect the inside of this contour path that we might have our H field being symmetric. Right, so inside of the contour path, there's this total current and some symmetric, probably some symmetric H field. So let's use the Ampere's law to solve for this. And then it seems like too, right, we could keep expanding this all the way until we get to this point, right? And at this point, once we get our contour all the way out to here, the symmetry is going to be broken. So let's use Ampere for here. And then once we get to this area, in the air between the semiconductor and the metal cylinder, we will have kind of two ways of thinking about this. And one is due to the this line current, and the other is due to the this volume current density. So it's probably going to be easier for us to solve for the H field due to the line using the line current with Biot-Savart, because it is not symmetric or centered at the origin. Okay. And then the combination, right, the total will be H1 plus H2, where the line current, right, we might call this, we'll say that the line current gives us H2, and the semiconductor give us H1. And then what about this part outside of the middle cylinder? What will happen when we go outside? So once we've made it all the way outside, out to here, what's going to happen? What's happening out here? Will we have a magnetic field outside of the cylinder? Give me a thumbs up for yes, thumbs down for no. All right, Calvin, thumbs down or thumbs up? All right, AK, okay, got Cade. What about you? AK, what do you think? Thumbs up? Daniel, thumbs up, thumbs down? What do you think? Magnetic field exists, yes, or magnetic field exists, no? Got Gabriel saying no. Okay, 3 yes, 3 no. So let's think about what's going on here. All right, so y'all know about coaxial cables? You have one connecting like maybe your internet or your TV?
Yeah.
Yeah. So coaxial cables, and I promise this is going to make sense in a second. Coaxial cables have an inner conductor and an outer conductor, right? So when you plug in, on your TV or your cable box, right? You've probably looked on the outside. There's it's hex, right? So you got something like this, and it's metal, right? And then you got an inner pin, right? There's that pin on side of your on your coaxial cable. And this is also metal. And it might be kind of hard to see, but if you look at one of those, have you seen what's surrounding it around this metal pin? Usually looks probably kind of white. It's sort of some kind of dielectric. Okay, so this is a transmission line with an inner conductor and an outer conductor. And what happens on these when you ground them is that you have this inner area that's a semiconductor, and so it insulates the inner conductor and the outer conductor. And so the inner conductor, if you have a current on this, and then you ground the outside one, right? What this means, if you ground this, let's connect this. Let's imagine this being connected to the rest of a circuit. Some load. We don't know what it is. This is your TV. Okay, how about that? This is your TV. All right, so now you have a current and a load. So what's going to happen? What's the current going to be on the outer conductor here?
Around there, wouldn't it be 0?
Okay, so the current will go through here and somehow go down to 0. That's one possibility. What's another possibility? What else might happen when we go through the load? We're just connecting it through in series. So we have current here, goes through the load. All right, we got this current here. What happens to the current outside of the load? Basically, if you have items in series, what's the current? Same or different?
It's the same.
Mm-hmm. Exactly. So you come through your load. It's your TV, your cable box, whatever. Now you got a current here. So this current is the same, right? It just goes through the inner conductor, through your load to the outer conductor, and then it's grounded. So you have a current that's equal in magnitude, right? These are, we haven't defined these quite yet, but they're equal in magnitude, right? We know that the current in the inner conductor is the same as the current in the outer conductor. Everyone feel good about seeing that? Okay, so now let's add in another step. Let's add in a direction. So now, okay, boom. Now we got current that is a vector. And they're in the same direction, right? The cable, it's collinear. So for simplicity's sake, now we can see they have the same magnitude. But I1 is in positive Y, whereas Y2 is in negative Y. Okay, so they have equal magnitude, but opposite direction. Right, so equal magnitude, opposite direction. You have one going this way, one going the other way. And what this does is that you end up with outside of this, once you get outside here, these two currents, they're actually creating magnetic fields that cancel each other out. Right, so this one is making, so put your right hand right up like this. You can see you got some current, right? It's going, wait, is my video mirrored? I don't know. We'll see. So, but if we put your right hand up, right, you got your thumbs. like this. Your current is pointed in this direction. So this is where your H is, H due to 1. But then if you put your right hand on the other one for I2, your H is in the opposite direction. So in this, for a coaxial cable with an inner conductor and an outer conductor, when you ground it outside of the cylinder, you're going to get a case where you have no magnetic field. So how does this make sense, right? Let's go back to the question in the text. We have a inner conductors and outer conductors. And so when we ground the outer conductor, there's going to be a current on this outer sheath that is in equal magnitude to I1 plus I2, but in the opposite direction. So outside of the metal cylinder, there is no magnetic field. All right, questions on that? So this hopefully this gives you an idea now too why coaxial cables appear in so many places as well. All right, so let's move on and let's work on this problem. So I'll give you a few minutes now. So I think you've learned a lot about how to solve this problem. So try solving for a magnetic field for the current in the semiconductor, and then try solving for a magnetic field for the current in this line. All right, so I'll put you into some breakout rooms and give you some time to work on this, and we'll then come back in, I don't know, maybe 20 minutes, and we'll spend the last 15 on the boundary conditions. So, all right. Put you all in breakout rooms. And I think they should be open now.
Okay, so this is indefinitely. Okay.
All right. How are you guys doing?
Pretty good.
Questions?
So Kate had a good question. So as far as like the electrical, not the electrical, the magnetic field for the semiconductor, it's only, is it 0 to 1 or 0 to 3? Because 0 to 3 would make sense as far as when you're going to add it to the other one.
Mhm.
But if we're only trying to find it inside the semiconductor, 0 to 1 for part A, it makes sense.
Yeah, so you will want, I guess, two different, you might want two different cases. One for the inside of the semiconductor and one for outside of the semiconductor.
So
because you're talking about the integration limits on R, or what is that what you're referring to?
yeah, the integration limits on R.
Yeah. So yeah, I think you can do it in two ways. One where you have inside the semiconductor and then outside of the semiconductor with two different limits.
Okay. And so this is another part that confuses me. So like this is obviously like a cylinder, but we're just negating the DZ because it's indefinitely long.
Okay. So yes. Okay. Yes. So on Ampere's law, why are we not considering the infinite length? Is that the question?
Yeah.
Okay. So because it's infinitely long, we can expect the magnetic field to be the same in each place. And that has to do with, right, if we have a, let's consider some really basic case like this. For all of these, right, if we want to know the magnetic field here, which we know is going to be in this direction, in the phi direction. But we get to there from some cross product, right, that has to do with the vector, the source and the point. And so we can see that the contribution from this section of the contribution to the H field from this section would be negated by the contribution from this section due to the symmetry aspect. And so this occurs for the infinite case, but not for the non-infinite case. It occurs for symmetrical cases. Yeah. If your current started here though, and let's see here. Went way up here, right? Now all of a sudden you have something here, but there's nothing else here that's equal but opposite as far as the contribution. So it's a little bit more complicated with the H field, right? Because we have to we're taking the cross of this current with the field direction, that RS vector, RSP, sorry, to get some other H. But so it's a little bit more simple with E field, where, right, the E field is easy, right? You make these two vectors, but in the H field case, it's like you have one this way and one the other way. These are getting very confusing, but one in one phi direction, one in the other phi direction. They have, they'll cancel due to the symmetry aspect. I think, I'm just rambling now, I think. Does this make sense?
Yeah, it does.
Okay. Cade?
Yeah, it makes sense.
So for the infinite case, that's how we can basically say, okay, well, it's infinite. So we're just choosing at any given slice. It's infinite. So at any given slice, you have this equal contribution above and below for any given slice on in an infinitely long case. And then because it's infinitely long too, no matter what that slice is, right? We know our H fields are in that phi direction. So our H fields aren't even pointed in Z. So it doesn't really matter where we're at in Z. Because the H field from the inner conductor, right, that's in phi. And then if you go out to that line, right, you have another H field that's in phi. It's in phi around that line. So it's the phi is not mapped to the origin, but it's still wrapped around that line. So you have two phis, but you could convert that to X and Y. And both of them will be an X and Y with no Z component. So for this problem, it does get a little tricky. I think what it ultimately means is it's a little easier to solve this problem in X and Y, because then you will get the same X and Y vectors rather than the cylindrical coordinates, which had slightly different coordinates. So
You suggest we use the X and Y?
Yeah, I would suggest using X and Y. And then, I would suggest using X and Y. Because I think I also, I would suggest using X and Y coordinates, actually. Either solving in cylindrical, if it's convenient, then converting to X and Y, or solving in X and Y. I'll leave that up to you. I think personally, I think it will be easier to solve for the inner one using cylindrical and then converting the inner one to X and Y, and then solving the line one in X and Y from the beginning.
So as far as our answers will always have like an R in them, right? Probably not a phi, but an R.
Well,
in this case,
you can convert the R to X and Y as well. So if you solve it in cylindrical, when you convert to X and Y, your R should end up being like X squared plus Y squared. Something like
right.
that. Yeah. All right.
I'm close. So
okay, I'm gonna go to another breakout room then. So I'll see you in a few minutes.
Like right now, I guess I'll just review double just to catch up.
Mm-hmm. Well, I hope you feel better, because
Thanks, appreciate it.
mm-hmm.
Hi, AK. Hi, Mario.
Hello.
Questions?
Don't think so. I mean, we both arrived at the same answers.
Okay.
So I hope we did it right.
Okay. Yeah, I think the other group that I was just talking to, I think my suggestion is that it might be easier to solve for the inner one in cylindrical and convert it to Cartesian, and then solve for that line current beginning with Cartesian. But you can do it many different ways. So yeah. All right. Well, if you guys don't have any questions, I'm going to go to the last one and then bring everyone back together. So any last minute questions?
I don't think so.
Yeah, I think we're gonna be okay.
Yeah. All right. Good. You feeling okay, AK?
Yeah, better than the last days and weeks.
That's good. Yeah,
Yeah.
that's good. All right. Were you able to, I haven't looked at, were you able to submit the homework today?
Yeah, I did the homework and the quiz.
Great.
Yeah.
All right. Do let me know if you want to set up another time to catch up on anything. So just send me an email.
Sure. Yeah, I guess this week I'm just trying to catch up with everything right now, and
Okay.
hopefully I'll try by today or tomorrow to let you know.
Okay. Sounds good. All right. Well, I'm going to go to the next room then. All right. Hi, Gabriel. Hi, Daniel. How are you? Any questions? Anything I can help you with?
Gabriel was just trying to explain because my answer got still had than Z hat.
Okay.
And he was saying like it cancels out from the equation.
Yeah, you should not have Z hat. And one quick way to realize that is just what is the direction of the current in both of these? It's in Z hat, right? So put your thumb in the Z hat direction and your fingers, right, will be in phi or X and Y, some combination of X and Y.
Can I ask how we find the RS, RP for the line current?
Yeah, I think so. There's many different ways to solve this one, but my suggestion that I think might be a little bit easier is to solve for the inner semiconductor using cylindrical coordinates and then converting the cylindrical coordinates to Cartesian. And then for the line current, solve that from the beginning in Cartesian coordinates and then combine the two answers using superposition. So I want to tell that to everyone. So if I think I'll bring everyone out into the breakout rooms unless you guys all have any questions right now.
How do we define the RP?
Yeah, so the RP will be from the origin to, what if I think it's 2, at 0.22 in X and Y.
RS.
And then RS will be from the origin to, I think it'll be in the X direction, it will be 2, and in the Y direction, it will be 2. And then in the Z direction, it will be Z, because the Z value can change.
Okay.
So if we are using that for RS, what would P be?
So the RS, the RS will be, and the P will be any point you're interested in. So some XP and some YP, like some variable that you aren't integrating over.
Oh, so we were not given a specific point.
Yeah, we are not given a specific point, but it could be anywhere in the inside of there. All right, so I think I'm going to bring everyone back together. All right, so while people are coming in, I'm just going to start writing out a couple hints. All right. So as you are all joining me, I'm just writing out a few hints that I think will help you all solve this. So for the inner semiconductor, right, this inner semiconductor, solve this. I think the easiest way is to solve it using cylindrical coordinates and then converting to Cartesian coordinates. And then solve the line current using Cartesian. And the RSP, right, this one should be somewhat self-explanatory. So it's in the X and Y. And let's just assume Z equals 0. So for all this cases, we have to assume we're at some, because we have an infinitely long cylinder, we have to just assume we're somewhere. So let's assume we're at Z equals 0. And then for RP, we're interested in any point inside of the, in any point inside of this outer metal cylinder. So let's call that some XP, YP position. Oh, 1 point, sorry. This should be Z, I apologize. The source is at any Z, whereas the point that we're assuming, we need to assume we're at some slice of Z. And we need to assume that we're at the same slice for both the semiconductor and for the line. So for both those, let's assume the slice is Z0. But when you're solving for the line current, don't forget that the source is from -infinity to infinity, and you will integrate over this variable. All right. And then when you get to this part, you can combine H1 plus H2 in Cartesian coordinates. All right, any questions? Do these hints help?
Yeah.
Okay, great. All right, so now let's go on and let's look at some boundary conditions real quick before the end. And these boundary conditions, the boundary conditions for magnetostatics, they are different than electrostatics, but the way that you solve them ends up being somewhat similar. Okay, so you have an XY plane that separates two magnetic media with magnetic permeabilities, mu1 and mu2. So if you like, Pokemon, right? This is the problem for you with Mewtwo. And there is no surface current at this interface, right? So right here, we have no surface current on the interface. We don't know anything about charges on the interface. We have H1 defined as this. So H1 up here, we have it in XYZ, and what we want to find is H2 and these two angles, and then we'll evaluate H2 and theta1 and theta2 when we're given some information about the H1 magnitudes. Okay. So this first one is you're looking at this problem just without any variables. And then in the second part, you are going to put some numbers to it. All right, so let's take a look in the, let's pull up the book, and we should have, there should be another table in the book so that we can find that tells us the boundary conditions. Okay. So I'm going to pull up the book here. All right, so are you seeing the book now?
Yeah.
All right, so we have the magnetic boundary conditions. And in this section, it describes kind of how they come to how they get to the boundary conditions. The description of the boundary conditions, right? One of them has to do with, remember, we've just used Ampere's law, right? Where we were taking a closed contour integral of H. And if we took that closed contour integral of H, we would get a current. And so that's what we just did in Ampere's law. So one of the boundary conditions has to do with the fact that if you have a surface current and you make this loop smaller and smaller and smaller, you can get some current, right? So you can solve for currents on a surface, which is a boundary condition. So in the electrostatics, right, we could find charged surfaces, right? Charged surfaces gave us different electric boundary conditions. For magnetostatics, surface currents can give us different results for our boundary conditions. And let's see here. Yeah, okay. So basically what we end up finding is that for the magnetostatics, right, the tangent fields are going to be the same. So we have tangent fields being equal to each other in magnetostatics, which is the opposite, right, of electrostatics. So electrostatics, we solved for the tangent field because that changed, whereas the normal did not change. And then in this, we are solving for the tangent fields. All right, and then the normal fields, we have this boundary condition. So I'll paste these into problem and let's use this information. All right. All right, so on your paper, see if you can find expression for H2 using the knowledge that we got here. All right, so in the X direction, so this is the XY plane. So what is, maybe start back again. So for this plane, what is normal?
The z-axis.
Yep, Z is normal. So that must mean tangent is X and Y, right? So this plane is the tangent plane. All right, so since we know Z is normal, so what should the magnitude in the X direction be for H2? All right, so let's back up even further. What is H1t? So the tangent plane is X and Y, so what should H1t be?
It's the x and y portion of h1, so it's the x hat h1x and plus y hat h1y.
Yep, exactly. All right, so if we know this, right? So what should the X be here now? So for H2, what's the magnitude in the X direction?
Negative H1. Sorry.
Like this? Yes?
Yes.
Okay. And what about Y? What's the magnitude?
It's the same H1Y.
Yeah, exactly. All right, so now we get to this last part, the Z. What is the Z going to be? What is the magnitude?
Shouldn't it be like mu1 divided by mu2 h1z?
Yep, yeah. And we got there right from starting like this. We have H1Z. So if you solve this, like this. All right. So now we have an expression for H2. For theta1 and theta2, what should we do to solve that? Solve for those?
You can just do the dot product.
Yeah, you can do the dot product. You can use a tangent. There's a few different ways to do this. One way, but basically any way you want to find this. But we already know from this, right? We know this angle theta, and we can, there's more than one way to do this, but we can write H1Z is the magnitude here. And then we can also, find this tangent right here. So this one, H1 tangent magnitude, which would be right, the tangent magnitude here is H1x squared plus right. So you can find the angle any number of ways once you come up with this triangle. And same too, whatever your, you have your z-axis continued, and whatever your H2 ends up being, right, you'll have some theta 2. Okay, and then for these, right, basically part C, just use the So this one is going to be, right, just an expression. Non-numerical. And then in this one, in part C, you will just plug in you have all these values now and just plug them in. So that's how you arrive there. All right, so magnetic boundary conditions, not too tricky. We've seen them with the electric. The magnetic ones are not too different. You just use these two things to guide you, and you should be able to solve any magnetic boundary condition problem. And the last problem, the normal, it's a little bit trickier. Like the normal is on an angle. And of course, I know you all took vector calculus, so I know you could find the normal vector if you wanted to, but I just wrote in the problem statement, I wrote in what the normal is. So that should help you out quite a bit. All right, so next week, Tuesday, you will have quiz and homework due. And then next Thursday, we will begin talking about the generator project. So hope you all have a nice weekend, and you're welcome to take off now. If you want to stay, we'll stick around and answer any questions you have.
I have one quick question.
Yeah, shoot.
I was looking back at the past notes of yesterday or of Tuesday.
Okay.
And I see the formula, the magnitude of the I vector, the current, is equal to 2 pi r h of phi. And so that's true everywhere you use Ampere's law?
I think I know what you're talking about, and this is for the cylindrical case.
Okay. So, okay, if it's not for the cylindrical case, then you just use the different, whatever one you need based on the shape.
Yes, yeah.
Okay. So we should technically be using it on question 2 as well.
Yes, yep, because it's also cylindrical. Yeah.
Okay. That was my only question. Thank you.
Yep. Yeah.
So I have a question about the example we just went through.
Okay.
So where is the direction of H1?
H1. So in this, we don't know necessarily what
H2 rather.
Oh, that's what you'll solve for.
So this is my. So we know the tangent, right, which is H1t. We know it's on the XY plane. You know the normal is on the Z plane. So we just come up with the equations for H2 without knowing where H2 is.
Yes, yeah. And actually, I kind of messed up. It should be something, when I drew this, it should actually probably be, oops, it probably ends up being something like this. Okay, so think you probably in your physics class and probably just in normal life, right? You've seen like a wave, you know, have you ever looked at a pool, looked down at a swimming pool?
Yeah.
Right, like this, you look down and then the light bends at the index. Okay, and that's because we have in the air ER1, and here it's like, I don't know, 80. Okay, so in both cases, right, the light in this problem and in this problem, they're very similar. Your wave is going through something, it hits a boundary, right? This is your pool. So this is their boundary. That's really what all of these boundary condition problems are, is you have a wave traveling, it hits a boundary. What happens when it crosses the boundary? And it'll always be controlled by epsilon 1 or epsilon r and mu r.
Got it. Thank you.
Yep, you're welcome. Anything else?
That'll be all.
All right. Thanks, Daniel. Hope you have a nice weekend.
You too. Sorry.
Oh.
So I didn't know our assignment would be due Tuesday, but I'll be going so I'm in the army and I'll be